I can do exactly the same kind of procedure, a change in oxidation number method, and do it for bases as well. So I'm going to come back to my permanganate, and I'm going to react it again with iron, this time to make not Mn plus 2, but rather MnO2, which is that kind of brown precipitate. And I'm going to make iron plus 3. So this is the reaction I'm going to balance. I have been told that it's in base, so I'm going to perform this process as if it's in base, knowing that everything else is going to be exactly the same in terms of my steps 1, 2, and 3, but I'm not going to do step 4. I'm going to hop down and do step 5, which tells me that for every oxygen I'm deficient, I don't just put an equal number of waters on the opposite side. I put 2 hydroxides on the opposite side, because remember, I'm in base, and then I counter it with waters on the opposite side. So notice in step 4, I balanced waters with protons when I was short oxygens. Now I balance hydroxides with waters because I'm working with base. So let's just work this problem. Step 1, the oxidation numbers. This is plus 7. This is plus 2. This is plus 4. And this is plus 3. So this is a 3-electron process here. This is a 1-electron process here. This one gets multiplied times 3. This one times 1. Therefore, when I'm all done here, I put a 3 in front of the irons, not a 5, and a 1 in front of the permanganate and the manganese dioxide. Now it's time for me to balance the deficient oxygens. This one's a little bit more complicated because I've got oxygens on both sides, but I've got 4 here and I've got 2 there. According to that little rule, I'm supposed to put double the number of hydroxides on the side that's deficient. So I'm deficient by 2, so I'm going to put 4 hydroxides here. Don't know why, they told me to. I'm good. And half that number of waters on the left. That sort of makes sense when you think about it because, you know, just from a stoichiometric perspective, if I am going to be having to balance my hydrogens later in the water, and there are twice as many hydrogens as there are in the hydroxides, I can see why I have to do this doubling here for when I come back the other direction. Well, I'm now balanced, or at least that's what they say I am. So let's see if it worked out. Let me write this down nice and free and clean of all of my work. So this is balanced. I've got 4 hydrogens, 4 hydrogens. 2 and 4, that makes 6 oxygens. 2 and 4 makes 6 oxygens. 1 manganese, 3 irons, 3 irons. Now the charge. Does it all add up? That's a -1 charge. That is a +6 charge, so this is +5 overall. This is a +9 charge. That better be, oh, what do you know? +5 overall. So my mass and my charge balance work as well. So summarizing what I've shown you here, you now have the ability to balance redox reactions. There's no substitute for practice in doing these and being exposed to some of the little tricks that sort of pop up every once in a while. But in the end, once you get comfortable with doing this, you'll have no problem balancing the vast majority of the redox reactions that you're confronted by. I will mention that some of the things that make for a little bit more complications are things like when you turn out to have more than one atom sitting inside a compound that's going to be contributing in a redox process. So for example, right here, you see that you've got chromium, which is a +6 oxidation number, and that's a +3 there. So that while you see that this is a 3-electron process, because there are 2 chromiums, you've got to multiply that times 2 to make a 6-electron process overall, even before you do the half reactions. So that's one trick that you need to be aware of that pops up every once in a while. The other thing you need to be aware of is that there are certain kinds of processes that do what we call disproportionation reactions. Here is hydrogen peroxide making water and oxygen. Notice that oxygen is present twice in this system. Here it is -2 here, and here it is -2 here, and 0 there. So it's not such a simple thing for us to balance this reaction, because I have now the opportunity for this oxygen to be used in more than one way in terms of its redox processes. In one case not being reduced at all, and in one case being reduced. So that simple change in oxidation number method that I talked to you about before doesn't work readily with disproportionation reactions without understanding a little bit more. I'm not asking for this in the processes that you're going to be trying to balance, so you won't see any disproportionation reactions when I show them to you on the exams, but they pop up every once in a while when people are trying to be particularly contrarian.